Yo, what's going on, guys? Today I want to talk about IV infusion, in particular the FSS, which is the fraction of the steady state. So yeah, fraction of the steady state. And I also I got a lot of positive feedback on my videos, so I want to thank you guys. Yeah, hopefully I can keep making more of these until you guys find my voice annoying. People have told me my voice kind of sounds like an angel, and then other people have said it's mad annoying, so, you know, haters gonna hate, but alright, whatever. So IV infusion FSS. Alright, so let's say I kind of drew the graph of an IV infusion, and this is what it is. You know, we have it goes up and then it flattens out, right? So I took the liberty of picking a few points on the graph, actually. So I picked a point here, I picked a point here, and I picked, you know, a couple points on this steady state, you know, the flat line. So what is this first point? This first point is just concentration at a certain time, right? It's concentration at a certain time. What's the second point? It's another concentration at another time, right? So I made it CT prime. Okay, so what are these points then? These points are all CSS, right? So no matter where the points are on this flat line specifically, they're all going to be CSS. Okay, so in that way, we know that the drug level in the body is never going to exceed CSS. Will never exceed CSS. So in that way, we can kind of call CSS, you know, 100%, right? We can do that, right? So what about these data points? What about CT and CT prime? So let's just take CT, or we don't even have to write the T. Let's just take C, and we can call that X%, right? Because it's not at 100 yet. It's still a percentage away from 100. So let's call that, you know, X%. So what is this exactly? This is exactly what FSS is, a fraction of the steady state. C is a fraction of 100%, or the steady state concentration. So how do we apply this, actually? Like, Xiao isn't really going to give us, you know, Xiao's going to say, like, okay, he's going to give us C, he's going to give us CSS, calculate FSS. That's too easy. Xiao's going to do what Xiao does, and, you know, just throw a random ass curveball at us, and hopefully with this video I can help you guys, you know, kind of navigate your way through those. Okay, so this is really how Xiao is going to give us problems, and I'm going to kind of give you an equation to tackle most of them. And I want to start with the IV infusion equation. The IV infusion equation, which is this, you know, C is equal to K over KB times 1 minus E to the negative KT, right? And the steady state equation, which is CSS is equal to KO over KB, and we know that this is the actual equation because steady state only occurs when T is huge, right? And when T is huge, well, we know E becomes super small, right? So E becomes almost 0, and then this is just 1, so it cancels out, so then we just get this. Okay, so now I want to do something. I want to do something that's kind of cool, and you take, all you do is, you know, you notice that there's a KO over KB right here, and then you notice there's a KO over KB, and just to review, KO is the rate KO is the rate for rate of infusion, which is 0 order, and K is the rate constant of elimination, which is in first order. Okay, so anyways, I'm just going to take KO over KB, and I'm going to plug it in. So we just replace this whole thing with CSS. That's all I'm doing. So C is equal to CSS. You guys see how I did that? It's not that bad, right? Next, what I'm going to do is divide by CSS on both sides. So divide by CSS on both sides, this cancels out, obviously. And we get a C over CSS. It's pretty simple, right? Is equal to 1 minus E to the negative KT. And what did we say before? We said that C over CSS is equal to FSS, the fraction of the steady state. So we can also say that this is FSS, and this is really the equation that we want, the equation that we're going to work with. FSS is equal to 1 minus E to the negative KT. Okay, so here's a practice problem. It's from the book, but I kind of changed it up a little bit. And it just says calculate the time needed to achieve 95% of the steady state concentration when the steady state concentration of drug X is 10.8 milligrams per liter. Drug X is administered at a rate of 30 mg per hour to an adult patient having K of so and so and V of 28 liters. And I added this too. We could worry about this later. I just wanted to prove how we found CSS in this equation. Okay, so let's see what we have. Right, that's always what we do. We see what we have first, and what we have. Let's read it. So calculate the time. They obviously want us to calculate time, right? Needed to. Let me use a different color. This is pretty bad. All right. Needed to achieve 95% of the steady state concentration. So 95% of the steady state concentration, right? So CSS we know is 100%. Now we want 95%, right? So C has to be 95%. So we can also say that this is FSS is equal to 95 over 100, which is 0.95. Okay, so we know that FSS is 0.95. When the steady, so we're actually given the steady state. So we're actually given the steady state. So drug X is administered at a rate of, so this is, we know that IV infusion rate is right here, KO, right, rate of infusion for it's 0 order. So we know KO is 30 mg per hour. We know the adult patient has a K of 0.099 per hour and a V of 28 liters. Okay. And here's something cool to know. It says an adult patient having K of this and V of this. So these two are patient specific, right? We can say that, right? Patient specific, because patients have their own, rate of elimination, rate constant of elimination. They have their own volume distribution, it's patient specific. Okay, so let's see what our equation is. Our equation is FSS is equal to 1 minus E over e to the negative KT. And we see from this equation that we don't need a lot of information, right? So let's look at what we have. Well, we don't really need CSS, right? There's no CSS in here. All we have is 0.95, right? So we have 0.95 is equal to 1 minus K to the negative E to negative K, E to the negative K, sorry. And we know K is 0.099 per hour. And time is what we want to find, right? So we don't need this. We don't need this. We don't need this. We don't need volume distribution. We don't need all this. Like this, the equation is so simple, and we don't need all this. It's just extra information. So here's what I want to actually touch upon. This t is kind of going to be hard to solve because it's raised to a power, right? How do we, if it's raised to a power, we can't just divide it or multiply it. So the textbook gives us this equation instead. T is equal to, and this is the exact same thing. They just shifted around. They did some manipulation and they just shifted around variables. So this is what you get. You get t is equal to negative ln of 1 minus FSS over K. So they just changed this to make t more solvable. So let's plug everything in what we have. So t is equal to ln 1 minus FSS, as we found, is 0.9. Make sure FSS is always going to be under 1 because it's a fraction, right? Obviously. K is 0.099 per hour. And what do we get? T is equal to, alright, so K is about 30.2, 30.3, I would say. And units are in hours. So it takes, so if I were to draw a graph, right? C versus T. And the infusion curve. So CSS we know is 10.8 milligrams per liter. And in order to get, we wanted 95% of it, right? So 95%, this is 100%, right? We know this is 100%, this is 100%. 95% is that's about here. That's 95, roughly estimated. So to get to here, it takes about 30.3 hours. And we don't even need to know the exact concentration. All we need to know is that the fraction is 95%. Yeah, I mean, yes, if you wanted to know the concentration, you could calculate it. all you do is you do, you know, times 0.95. Yeah, that's it. And then I want to touch upon one more thing. Okay, so I just copied this from before, and I wanted to touch upon this last question, and I kind of made a mistake from before, so I fixed it. I wrote steady state as something else, but this is what it actually is. Okay, so how can we prove that CSS is truly, you know, 10.8 milligrams per ml? Okay, so we know the CSS formula, right? Just K over KV, because T is large. We're assuming that steady state is achieved when T is super big. Okay, so what do we have? We have KO is equal to, you know, 30 milligrams per hour. We know that K, you know, is patient specific, 0.099 per hour, and we know V is 28 liters. So all we did was you plug it in, and then we see if is the answer we get truly 10.8 like they claimed, right? They claimed that it was 10.8. So now we plug everything in and we see if it is, and lo and behold, if you plug it in, you get 10.8 milligrams per ml. So this thing really is true, you know. This thing really works, and they kind of just proved it to us. But remember, for fraction steady state, you don't need all this information. It's all extra. And all right, so yeah, made a video. Video is still over 10 minutes, but it's getting shorter.